Let's begin by talking about your monosaccharides. We will discuss 3 carbon to 6 carbon monosaccharides. And from our definition of carbohydrates, they are polyhydroxyaldehydes or polyhydroxyketones. We will start with your polyhydroxyaldehydes or what we call aldoses. So again, the functional groups that you will see include your hydroxyl functional group and your aldehyde functional group. We start with the simplest, which is called glyceraldehyde. So it has 3 carbons. So here in carbon 1, we have the aldehyde functional group. And then we see that there are OH groups attached to the remaining carbons. So you have one OH attached to carbon 2 and another OH group attached to carbon 3. Notice that carbon 2 is called a chiral center. When there is a chiral center, it means that there are 2 possible configurations for this molecule. In this drawing of your glyceraldehyde, we see that OH is on the right side of carbon 2. Hence, it is designated as D-glyceraldehyde. And this one is an absolute configuration and has been confirmed by X-ray crystallography. Let's move to your 4-carbon aldoses. Here we see 2 D-erythrose and D-threose. So we have the aldehyde functional group in carbon 1, and there are OH groups attached to carbons 2, 3, and 4. Notice that for your 4-carbon aldoses, you have now 2 chiral centers. Carbon 2 is a chiral center, carbon 3 is a chiral center, but not carbon 4 because it has 2 hydrogens bonded to it, therefore it's not a chiral center. And recall from your organic chemistry class that if you have n number of chiral centers, the number of stereoisomers generated is 2 raised to n. So in the case of your 4-carbon aldoses, you have a total of 2 raised to 2 or 4 stereoisomers, but here we only see 2, erythrose and threose. So where are the remaining 2 stereoisomers? The 2 remaining stereoisomers are your L-erythrose and L-threose. So how did we know that this is the D-erythrose and this is the D-threose? So we just follow this carbon, the second to the last carbon. If the OH is found on the right side of carbon 3, then it is your D stereoisomer. Means that if we draw the function or if we draw the structure of L-erythrose, it will look like this. This time your OH is on the left side of carbon 3. And if you wish to draw L-threose, your OH here should be on the left side of carbon 3. Now, most of your monosaccharides in nature occur as your D isomers, but not all. So there are some monosaccharides that occur naturally as the L isomer. Let's go to 5-carbon aldoses. So if we have an additional carbon, that means we have 3 chiral centers. So 2 raised to 3, that will give us 8, meaning we have 8 stereoisomers. And here we see half, which are your D isomers. So we have D-ribose, D-arabinose, D-xylose, and D-lysose. So the remaining 4 are the L-isomer counterparts of these 4 D-isomers. And if we go to your 6 carbon aldoses, we have an additional carbon. So now we have 4 chiral centers, which means we have a total of 16 stereoisomers. And here we see half of those. So we see 8 D-isomers, D-allose, D-altrose, D-glucose, D-mannose, D-gulose, D-idose, D-galactose, and D-talose. So again, if you want to draw the L-isomer, you just have to change the configuration of your hydroxyl group in the second to the last carbon or the last chiral center. Now, sometimes your monosaccharides are often described according to the number of carbon atoms that they have. For example, for your 3 carbon aldose, they are often called triose. For your 4 carbon aldose or 4 carbon monosaccharide in general, they are called tetroses. For 5 carbon monosaccharides, they are called pentoses. And for your 6 carbon monosaccharides, they are called hexoses. Now, if we are specifically talking about aldoses, then for example, D-allose is an aldohexose. Ribose is an aldopentose. Erythrose is an aldotetrose. And your glyceraldehyde is an aldotriose. Now, another possible functional group that can exist in your monosaccharides is your ketone. So in this class of monosaccharides, we call them ketoses. So again, we will discuss 3 carbon to 6 carbon ketoses. So we have the simplest ketose, dihydroxyacetone. So for this one, the carbonyl functional group is found in another carbon atom. So the important difference is that in aldoses, your carbonyl functional group is in carbon 1. But in ketoses, your carbonyl functional group is now found in carbon 2 instead of carbon 1. Okay, so our simplest ketose, which is a ketotriose, is dihydroxyacetone. And notice we don't need to designate it as D or L because it doesn't have a chiral center. So it loses its chirality due to the switch in the position of your carbonyl functional group. Next, we have our ketotetrose or our 4 carbon ketose, which is erythrulose. So this time, we have 1 chiral center, which is carbon 3. Therefore, we designate this as D-erythrulose because the OH attached to carbon 3 is on its right side. Now we go to our ketopentoses or the 5 carbon ketoses. We have, because we have an additional carbon, we now have 2 chiral centers, which means we have 4 stereoisomers. And we see here 2, which are the D-isomers. So we have D-ribulose and D-cellulose. And for our ketohexoses, so again, we have an additional carbon. So we now have 3 chiral centers, which means we have 8 stereoisomers. And here we see 4 D-isomers. So we have D-cyclose, D-fructose, D-sorbose, and D-tagatose. So if you notice the names of our ketoses, particularly our 4-carbon and 5-carbon ketoses, we see that their names are related to some of your aldoses. So erythrulose comes from erythros, and you just have that UL inserted. Ribulose comes from ribose, and cellulose comes from xylose. So you see the UL being inserted into the name, and that is a hint that it's a ketose. But for your 6-carbon ketoses, most of them were given their original name, the name attributed to them when they were discovered, such as sorbose, which is the genus of a certain berry plant found in some mountains, which is rich in this sugar. So again, your monosaccharides, all of them contain asymmetric, one or more asymmetric or chiral carbon centers, except for your dihydroxyacetone. And remember, a molecule with n chiral centers has 2 raised to n stereoisomers. So recall, your stereoisomers are mirror images of each other, but they are not imposable. So just like your left hand and your right hand, so they are mirror images, but if I superimpose them, they do not match. So again, most of your hexoses, particularly your hexoses in nature, so for example, your hexoses found in living organisms, they are D-isomers. Again, some sugars occur naturally as their L-isomer. So this mystery hasn't been solved yet, but their theory is that it's because the enzymes that first came into nature, because the enzymes that produce these monosaccharides were stereospecific. This also led to having sugars with a specific um, configuration. That is their theory. Now, there is a term epimer. An epimer is used to describe 2 sugars that differ only in the configuration around 1 carbon atom. So, for example, glucose and mannose are epimers because they only differ in the configuration of 1 carbon atom. So again, you have the aldehyde in carbon 1. But if you look at carbons 3, 4, and 5, the positions of the hydroxyl groups are the same. So for carbon 3, it's on the left side. For carbons 4 and 5, they are on the right side, but they differ at carbon 2. So for glucose, the OH is on the right side, but for mannose, the OH in carbon 2 is on the left side. So those are your epimers. So you will easily see which are epimers just by looking at the position of your hydroxyls. So they should only differ in 1 carbon atom. Now, there are several ways of depicting the structure of your monosaccharides, and the most commonly used is the Fisher projection formula. So in the Fisher projection formula, you use lines, so horizontal and vertical lines. So these horizontal lines mean that your groups, the groups attached to this carbon, are sticking out of the paper towards the reader. Okay? And the vertical line, so for this one, because it's the simplest triose, so this means that your aldehyde and this CH2OH or methyl hydroxy functional group, these are oriented away from the plane, away from the reader. So when you see a Fisher projection formula, that's what you will automatically, that's how you will automatically interpret these vertical and horizontal lines. Sometimes they use the perspective formula to prevent ambiguity. So again, you have here the solid wedges, which means the functional groups are oriented towards the reader, and you have the dashed wedges, which mean that your functional groups are pointing away from the reader. So if we look back at our Fisher projection formulas here, this means that for this one, let's take a look at the 4-carbon aldoses. So this one, let's look at carbon 2. So the aldehyde functional group is pointing away from the reader. And then the rest of this is also pointing away from the reader. So the OH here is pointing towards the reader. And now, for the bond between carbon 3 and carbon 4, this time, it's pointing towards the reader. So you see, it's like they are alternating. It's like the bonds along the central carbon chain are zigzagging. And this time, the OH and the hydrogen attached to your carbon 3 are pointing away from the reader. So the OH and the hydrogen attached to carbon 3 are pointing away from the reader. So you will, in this one, you have dashed wedges. So it's difficult to imagine if you are not used to the structures of your monosaccharides. So just imagine that the central carbon chain is zigzagging. So let's say this is the plane of the paper or the screen. This is carbon 1. Sorry. Repeat. So we have carbon 2, carbon 3, carbon 1, which contains your aldehyde functional group. This is carbon 2, carbon 3, then carbon 4. So again, they are zigzagging. So it means that, so you have here your OH pointing towards the reader. So if this is the plane of the screen, and then you have the OH and the hydrogen attached to carbon 3 pointing away. And then finally, so this is your last carbon. So this is your CH2OH. So this is what I meant when I used the solid wedges and the dashed wedges. So that's how you interpret your Fisher projection formulas.